Alright, sorry everyone for that delay. Mason?
Alright, so back to the original topic, I'll be repeating pretty much what Royal said. I'm doing thermal time constant. I forgot my group members' names, but I am part of group 2. I forgot my group members' names on the presentation line. Okay, so for the experimental review, other than maintaining a safe lab, our objective is to use the thermocouple to insert it and remove it to find the time constant through manipulating the data and using a graph to figure it out. So the thermal time constant represents how quickly a system responds to the sudden change in temperature. So procedure review, the first thing we're going to do is set up the thermocouple, the PDAQ. Just making sure it's connected correctly to the system set up to make sure it's going to record everything, and even maybe testing the ambient temperature before collecting any data. Then we waited for the water to boil, which was super fun. In that time, we discussed what we thought was going to happen and brainstormed. The beaker was filled about to that level with water and placed on the, what's it called? Forgot the boiler. And after that, once it reached a boil, we placed the thermocouple at the top and then sent it in. It started logging data pretty quickly after it entered the water, and the data appeared on the computer. So once after it boiled, we turned it off and let it start to cool, and we collected data. So for the lump compass method, it assumes the temperature within the object is uniform at any given time. This allows the object to be treated as a single node with no internal temperature gradients. The formula we use for the rate of heat convection to and from the system and the rate of change of the thermal energy within the system is shown. It's the basic heat transfer equation that we all know and love. When you integrate this equation using T equals time of 0, and when you look at the graphs, you decide when you think it is T of 0. It's you eyeball it, but the graph is pretty easy to read, which you will see in a couple slides. So once you set it to that, rearrange it, integrate it, this is the formula that we're given. So for the time constant, that half of the previous equation, Joel's left side, that is the normalized temperature. To find the time constant, we plot the time versus the natural log of the normalized temperature. From that graph, a line best fit, or a trend line, is going to appear. The slope of that trend line, y equals mx plus b. The m of that is equal to the negative inverse, or reciprocal, of the time constant. So the thermal time constant represents how quickly a system responds to change. A small time constant means the system responds quickly, while a large time constant indicates a slower. That I think is backwards. I also messed it up. A small time constant is a quick change in a large, no. Hold on one second. I've got the data. Okay, a small time constant means a quick change. It's a quick instant change, while a larger time constant means it's a slower change. Okay, I did have that right. I confused myself. So this is the raw data. This is all the data unmanipulated, just over time, the temperature. And this is, as you can see, this is where we started, where we dropped it into the boiling water. The immediate increase is pretty easy to see. So I selected that area as temperature of 0. I think I selected the point right before it started to really increase so that it showed really what was 0 and what was 1. And so then to show y'all better, this is the data split up over time. So this is it increasing, and that's it slowing down. These really should be reversed for better seeing, but I didn't realize in time. But yeah, I even have, this is the 2 points before the quote unquote 0, so that you can see it was pretty steady before a very quick increase, versus the very slow 300-second decrease for the removal time. So for the natural log of the normalized temperature with the trend line, this is, again, just taking that equation. I think my temperature of 0 was around 24.7 I think is what I aimed it for, using that to create that left side of the previous formula to plot this, and then using the trend line to get the value of the slope. Using the value of both slopes, we were able to get the time constants for both. These do line up, the small time constant with a very quick change, large time constant with a very small change. So it's larger during the removal than insertion. Air has a much lower heat transfer coefficient than water, resulting in a weaker convection. This significantly reduces the rate of heat transfer, causing the thermocoupled temperature to change more slowly. As a result, the time constant during removal is much larger than the insertion into the water. So the curve fit is kind of where I even think I started to confuse myself, but I was able to graph them. So series 1, the blue line, is the normalized temperature, while series 2 is the curved fit. And I did the same thing with the removal. So the data interpretation, as I've kind of talked about it as it's gone on, the insertion versus removal, the insertion had the smaller time change because it has smaller time change because it was so quick, versus the removal had a larger time constant because it was so slow. The experiment could have been messed up by doing it differently. You can never have the same experiment twice. Several reasons: human error, thermocouple placement, changes in boiling water, not really, but experimental errors. You can hit the wall of the beaker and, again, moving while exposed to time air. The time constant of the system can be changed by modifying the heat transfer coefficient, using a different type of thermocouple material, or changing the surrounding fluid. And here are my references.
Can we give a round of applause, please? Any questions
Oh, yeah.
for Missy?
Can I see your removal plot? I think the right plot is important. I mean,
Okay.
it should be decreasing rather than increasing.
What'd you say, sorry?
So it should be like this. In your curve is increasing, right? The right plot. Removal time versus natural log of the
Yeah.
So